Okay.
The next speaker is Rashad, who will tell us about an intrinsic exterior calculus formation of nonlinear elasticity and deciding underlying structure.
Okay. Thanks a lot for the organizers for organizing this very nice sessions. Unfortunately, so that was the initial talk, the title of the talk and the paper. In the end, we found a much simpler one and much more concise. So this is a paper that we just published yesterday. So it appears online. It's open access. So you can find all of the details here. It's about intrinsic nonlinear elasticity. So nonlinear elasticity done in non-standard ways, and I think it will combine a lot of what you've seen here if you've been attending here from the morning since the morning. And this is a collaboration with my co-authors Andrea, Federico, Erwin, and Stefano. So the focus of our work is the following. So we want to formulate nonlinear elasticity using exterior calculus. And we want to do that geometrically, and we want to do it in an intrinsic way. And I'll try, throughout the talk, I'll explain what these different notions mean. The main aim that we want to do is we want to emphasize and highlight all of the underlying structures of the equation. We don't want to look just as PDEs. We want to look at the geometric topological underlying structures. And why would you want to do that? The main motivation actually is to do structure preserving discretizations. I will not show any simulations here. We're not there yet. This is actually something we're working on right now. But first, so this is a purely theoretical paper just to try to find what kind of structure is there so that in the end, later we can aim to hopefully all or as much as we can. For nonlinear elasticity, we treat in this paper and in this work, the spatial, the material, and convective representations all at the same time. And this is one of the cool advantages that we're going to show here. Just as a reminder, so we do here nonlinear elasticity, but actually Navier-Stokes is a simpler, it's even a subcase of that, even simpler, because all of the strain stuff is much easier handled with the constitutive equation between the strain rate and the stress. So this is easily extendable to the Navier-Stokes. Actually, I'm more interested in the Navier-Stokes. This is where we started. We started in the fluids. We went to try to formulate it. Then we found actually nonlinear elasticity, try to do it for generic case. And then later we're going to go to the fluids again. So first I'm going to show you, remind you of the standard formulation of nonlinear elasticity. So this is the geometric formulation. So just as a recap, what we have is a body manifold, is an assembly of material particles that we call body manifold B. Through an embedding phi, we put it in the ambient space. And this embedding can actually, it actually consists of rigid body motion and also of deformation. And through a family of these embeddings, we just define a motion of a deformable body in the space. We can represent the nonlinear elasticity as using tensor fields either on the body manifold, which is called the body or the convective representation, or tensor fields on the ambient space, which is called the spatial or the Eulerian formulation. But also, especially in solid mechanics, the Lagrangian representation or the material representation, which goes to the configuration space, which here is an infinite dimensional manifold that corresponds to the space of embeddings of the body manifold in the ambient space. The corresponding tensor fields that appear in the material representation are always 2-point tensor fields. Yeah. Okay. So there is one point here that I want to highlight before moving on, is that here the body manifold is outside of the ambient space, and what we mean by that is that this assembly of body, this assembly of matter of body particles is not a reference configuration. So we don't here use a reference configuration, and I'll point out to that later on why. So the standard equations in the spatial representation are simply conservation of mass in the first equation, conservation of momentum in the second equation, and we have a constitutive equation between the stress and a strain measure. In the tensor calculus, in the standard formulation, the density is a function, a smooth function, the velocity is a vector field, and the stress is a 2-0 tensor or a second rank tensor, depending on how your favorite choice of indices. The energy balance is simply the sum of the the rate of change of the sum of the kinetic energy and plus the strain potential energy is equal to whatever is on the boundary. Here, we treat the generic case. We have velocity boundary conditions, we have mixed boundary conditions. So you can have on the velocity, and you have also the traction. So this is the generic case. One thing that we want to do, that we aim to do in this work, is try to do as generic as possible. So we do it in a coordinate-free manner. So we have, so you would see here the G is the metric of the ambient space. So we keep it generic throughout the work. We don't assume any Euclidean structure also in the ambient space. So we try to be as generic as possible so that we can identify at which level do we need the metric structure, at which level do we need the, is everything defined topologically. And one thing is to be coordinate invariant so that in the end, when we do a structure preserving discretization, is that the code works for all coordinates. We don't need to worry about Cartesian, polar, and whatever. So that's for the spatial representation. The convective representation is also another possibility. We get exactly this. We get another set of equations, but we get on top of that, we get an advection equation for the metric on the body manifold. So it does not have a body and metric by itself, but then it gets a time-dependent metric that's pulled back from the ambient space, and we get everything is exactly the same, but on the body manifold. Here the space of G hat. So G hat here is will actually serve as the strain variable. And it's also the metric on the body manifold, and the space that it has also a space of its own that's called M of B. So that's a space of Riemannian metrics on B in a geometric setting. So this is less standard, but in the geometric mechanics work, so this has been shown to be very powerful. It also provides some guidelines for designing structure preserving time integrators that actually are also to define hypoelasticity in more generic cases. And for the Lagrange representation or the material representation, we have also another set of equations. So all of these, they should be familiar. Now the drawbacks, and which is the motivation of our work, why we want to go to exterior calculus, is that because these formulations, these standard formulations on based on tensor calculus, first of all, especially in nonlinear elasticity, there's an abundance of mathematical representations. So there are a gazillion stress representations, another gazillion strain representations, and in the end, they should be related to to each other. And especially when we have the metric, we can design all sort of tensorial variants of these, which makes it even harder, which is a mess. So especially for starters or for engineers, it becomes a little bit complicated, while the theory in the end should be simple. There are also ambiguous transformations between these different representations. One, I highlight only the Payola transformation, which is standard to transform between these different representations. What we'll show here in the end, we never use it because it's just an artifact of these different representations, actually. One thing that we try to avoid using at all is an intrinsic body metric. So the capital G, usually in Hughes and Marsden book, this is arbitrary, actually. So it depends on a reference configuration. So I could choose one that's different from any other formulation. And so for some materials, even we don't have one reference configuration. You can have multiple reference configurations or stress-free configurations. So this is actually, there has been a lot of interest, and especially started by work of Knoll, trying to find what properties are actually intrinsic for nonlinear elasticity. Tensor calculus operations, they change drastically when we change dimensions or coordinates, but most relevant for discretization is actually the separation between metric dependent and metric free operations it's very hard to see in tensor calculus, and also the separation between orientation dependent and orientation independent operations, which is in line with what Chris presented in the morning. So this is our formulation of nonlinear elasticity. So this is only an overview. The paper is 50 pages long, so I'm sorry I cannot tell you all about it, but feel free to read it and we can discuss later. So this is the overview of the formulation that we have. So first, what you see, we treat the three representations, so the convective, the material, and the spatial representations. All of them will be represented using bundle valued forms. for exactly the same reasons that Chris mentioned in the morning, and for what I mentioned here about tensor calculus. So the convective representation will be vector or bundle valued forms on the body manifold. The spatial representation will be bundle valued forms on the spatial manifold, while the material representation will actually be 2-point tensors, and this is the power. So the value leg of the bundle valued forms will be in one manifold, will be in the spatial manifold, while the form part will be in the body manifold. And then once we said that, all of the transformations between the different representations become just one operation, which is the pullback. You just pull back either the form part or the value part, and it becomes very clear to do that. One other thing that we add here is actually we introduce the Hodge star. So the Hodge star will take us from the kinematic variables to the kinetics variables. So from the velocity, strain, and the strain rate to the stress and the momentum. So the Hodge star will be where all the constitutive equations will be. And then we have also the representation of the deformation on the space of Riemannian matrix. But we can also identify these by bundle valued forms, but there's no time to go into details here. So the formulation of nonlinear elasticity using, so just as a brief recap of exterior calculus based on bundle valued forms is that, first of all, they mimic precisely the scalar valued forms. So in scalar valued forms, so if you remember, there are sections of the alternating multiple of the cotangent space of the manifold. So that's the scalar valued forms. And we have the Hodge, the exterior derivative, and the wedge, and the integration by parts and Stokes theorem, all for scalar valued forms. They all transform to vector valued forms naturally. While just some with some differences, with the wedge dot actually will map a vector valued and a covector valued form to a scalar valued form. And we're going to have the Hodge also goes from a vector value to a covector valued form, and the exterior covariant derivative is generalization of the exterior derivative, and it combines it both. It combines the exterior derivative and with the covariant derivative. So this is just how our choice of the formulation of nonlinear elasticity. So we're going to have all of the kinematic variables. We're going to represent them as vector valued forms, while all of the kinetics variables will be covector valued forms, or more precisely, covector valued pseudoforms. And by pseudoforms, this is where the orientation makes its entrance. And we're going to have the relation between these variables using the Hodge star. So all of the constitutive equations will be formulated using the Hodge inside of the Hodge star. And then with the transformation between the different representations, as I said, we'll be just using the pullback either on the form leg, which is the subscript F, or with the on the value leg, which is subscript V. What do we mean by intensive and extensive? So thermodynamically speaking, an intensive variable is just a variable that does not depend on the size. So it's independent of the volume, while an extensive variable would have this dependency on the volume or on the size. And this is precisely what we need in order to show this duality between the intensive variables, or between the kinematics and the kinetic variables. So for the kinematics variables, for example, the velocities, so instead of looking them as vector fields on B or vector fields on S, or actually these funny, they're actually 2-point, so they're actually like a vector field over a map, which is the material representation. Here they become all vector valued zero forms. Acceleration is also time the differentiation in that, so their accelerations are also vector valued zero forms. Vector valued one forms are, for example, the velocity gradient and the deformation gradient, so and the strain rate. So all of these variables are naturally vector valued one forms. For the kinetics variables, we define them. So we define the momentum to be the Hodge star operator applied to the velocity field. So the Hodge star would take a vector valued k form to an covector valued n minus k pseudo form. So the momentum here is a covector valued n it's a covector valued n pseudo form. And by that, it's naturally how, and this is the extensive momentum. So it's naturally associated to like phases in the mesh, or like tetrahedral in the mesh, so volumes. And then when you integrate the momentum under some conditions, when you integrate the momentum inside of that volume, you get the momentum of this particle. So this is precisely how naturally we think of momentum being an extensive variable. While stress is naturally also based on the work of Eva Kenzo and others, it's naturally a covector valued n-1 form. So it's something that we integrate on the surface, and then we get the traction force naturally. And now the different representation, all of the different representations in the literature can be all boiled down to three variables. So either So the reason why we have an abundance in the stress representations is because sometimes we choose to put them, some of them the mass dependency, sometimes we put them, we do them without any dependency, sometimes we put the mass and the volume inside of them. The most famous ones are the convected, the first Payola, and the Cauchy stress tensor. So these they don't have any volume dependency, so they are intensive, but they have the mass dependency inside of them. If we divide by the mass, we can remove this mass dependency, and then when we multiply by the Hodge-star, or apply the Hodge-star operator, we can get these capital T, which are the extensive stress representations. The only one that has been formulated and been given a name has been attributed to Roger, because it's also related also to the space of Riemannian metrics, because on the space of Riemannian metrics, the Roger stress can actually be also seen as a covector of the infinite dimensional space of Riemannian metrics. So we can boil down these tensor fields to, again, so we can do everything actually using the infinite dimensional configuration space and the infinite dimensional space of Riemannian metrics. The others, they don't have any names. So if you, I haven't come up with them. So if you want to claim any of these, please feel free. So the equations of motion in the spatial presentation, so now they will look like that. So we have shown in the paper that these are, we have shown precisely that they are equivalent to the standard formulation. So all of the, you can backtrace how can you transform the standard formulation into these ones based on bundle valued forms. The first one, so there's a catch here. So it's not purely on bundle valued forms, because the mass, so when we apply the Hodge to it, so first of all, it was a scalar valued form. So it was a mass density function. When we multiply the Hodge, the standard Hodge, it became a top form. But we're looking actually into something that we can represent it also using bundle valued forms at the moment. But what you see here is that the first equation is the mass top form, is just the conservation of mass and represented in it. The second equation is the conservation of momentum, and you clearly see here that this is precisely in the conservation form. While actually and you also see the high resemblance between the nature of the stress being a covector valued n-1 form, and also what's inside of the bracket there is actually the momentum flux. So it's precisely the same nature of the stress. And the constitutive equation becomes very, very similar. What you see down there in the energy balance, what's very interesting is actually how, because of the use of the bundle valued forms, how the separation between the types of boundary conditions, they become very clear. So between the velocity boundary conditions and the traction boundary conditions, and exactly the rest are just differently looking equations, but exactly the same idea. What I want to highlight in the last, I think I have how much? 2 minutes. Okay, so in the last 2 minutes, 1 minute for the more underlying structures that's of these equations. So the exterior, the bundle valued forms, they also have an underlying the rump complex structure. While actually the pullback on the form or on the value leg, they define some bundle isomorphisms. So actually we can understand, or we can study, which is why we can study any one of these representations, and the rest follows. And this is a very good starting point for structure preserving discretization. We also have the double complex with the Hodge. We can define the co-differential operator also in the same way, and we can define integration by parts. So we can, it's ready to define a finite element exterior calculus or a discrete exterior calculus version based of that. One other thing that we shown in this paper that has not been shown in the literature before is actually there is principal bundle structure that couples the space of the configuration space, which is the space of embeddings, to the underlying space of Riemannian matrix. And this principal bundle structure is also very important for discretization. It all has been used actually to define time integration, geometrically consistent time integrators. And it also is very important to define objective rates of the stress and strain. And in the end, there has been a very recent work showing actually that all objective rates in the end are just covariant derivatives on this space of Riemannian matrix. But also the principal bundle structure is very important to actually, maybe we can try to decompose using an infinite dimensional connection. We can try to decompose the motion into different components. So that's the end of my talk. So the conclusion is that we formulated nonlinear elasticity using bundle valued forms. The take-home message is that intensive variables are naturally vector valued forms. The extensive kinetics variables are naturally co-vector valued pseudo forms. We emphasized a number of underlying structures that I shown very briefly. And the next step is what we're doing at the moment is actually using for discretization and for Navier-Stokes in particular. So this is the paper. So as I mentioned, it's very freshly just published yesterday. So you can look at if you're interesting, you find it interesting, and please, any feedback is welcome or discussions. Okay, thank you very much.
This is our last one, so we have plenty of time for questions. So when you do these formulations for problems like Navier-Stokes or fluids, how does it change? What are the difficulties that don't appear in the nonlinear elasticity case?
If you mean with the fluids,
yeah,
it's exactly the same. Oh, so with the fluid, so the only difference going from the fluids to the going from the nonlinear elasticity to the fluids is, first of all, we don't have the convective presentation due to its topological. We don't have something called a convective presentation in the fluids due to topological reasons of the diffeomorphism group. So that's so we only have the Lagrangian and the Eulerian representations. Another thing that we have also for the fluids is that the space of Riemannian matrix there becomes we don't need it because we don't have any strain. We just have the strain rate in the constitutive equation. So in the equations here, so the constitutive equation between the stress is no longer between the stress and the strain itself, but with the strain rate. And the strain rate is simply here was the symmetrization of the velocity of the covariant derivative of the velocity field. So in the end, so we only have velocities and we don't have a strain. For viscoelastic materials, then we can actually go. Then we're gonna come back to the case of nonlinear elasticity.
Good question.
Yep.
So I guess like a philosophical question. So there are lots of different isomorphisms between different types of objects, bundle value forms, or different types of tensors and stuff. What is it that you really like about the bundle value forms perspective that other geometric perspectives wouldn't be?
The discretization. They are naturally ready for the discretization. When we talk about the forms, then they are naturally. So when we highlight which is the form part and which is the value part, we already know that this is the form part. If it's a one form, then it's naturally associated to lines. If it's a two form, then it's to surfaces and so on. So once we identify that, and then you get immediately what should be the correct spaces. Another thing which is actually due to the duality, something that I did not point out here, but all of the equations. So the previous equations I showed them written in tensor calculus, so the standard formulations, but you can also write them in bundle valued forms. So you can write the intensive representation of the equations are using bundle valued forms, and the extensive representation of the equation using also bundle valued forms. The Hodge duality that you see between these two it's completely hidden in tensor calculus. You don't see it. And once you identify that, these are precisely the basis of the dual field method, for example, that Arthur displayed. And this is also the basis of what Chris displayed in the morning, that actually want to identify where do you want to put the discrete Hodge stars between the two variables. And also the basis of what Mark showed here on for the spectral element method. So again, so you just get the discretization becomes much natural. Another thing that you get also for free is the choice of finite element spaces. So all of the compatibility is already in this plot. So all of the so the complex property that you get from this figure in here is precisely that tells you how it just narrows down the choice of finite elements or whatever basis that you want to choose, so that you can know what kind of compatibility that you have. Here, there's one thing that I did not mention, is that actually the exterior covariant derivative does not square to 0, but it equals to the curvature. And then again, so with this insight, you can also see how you can include the curvature into the game.
Okay, let's thank Rami again.
Okay, thank you very much.